All right, let's start. Good morning. I'm going to take attendance today. Let's start with you. So on Friday this week, we're going to have our first midterm. Last Friday, I was able to upload a guide for it on Canvas. So if you go under the Assignments tab, and if you go to the assignment for midterm 1, you should be able to access it right now. I wanted to ask you if there are any questions or concerns about the first midterm before I get started today. So what's going to happen this week is we have a bunch of things to cover. You're still responsible for these topics. So I'm not going to spend that much time on the optional computer graphics business. They have a bunch of interesting stuff, perspective projections and so on. So we're not going to do that. From a computer, hi.
Morning.
Morning.
I cleaned the whiteboard.
Thank you.
Tomorrow is Tuesday.
Yeah.
And today is Groundhog Day, everybody. Because we're getting close to Valentine's Day and President's Day.
Yeah, thank you.
Is everybody excited? Okay. Every day.
Thank you. Groundhog Day. I should watch that movie again, I think. It's a pretty nice movie. Okay. What were we saying? Oh, okay. In computer graphics, it turns out that it's important to be able to render a 3D thing, a scene, for instance, but then to sort of project it and figure out how it looks like in a two-dimensional plane so that people can play video games and stuff like that. It's a really interesting topic. They mention it in the textbook, but we're not going to go into that. I think I'm just going to let that slide. Though I do want to talk about this affine transformations, still useful within the context of computer graphics. That I'm going to mention a little bit. And 3 more items are going to be block matrices or partition matrices, elementary matrices, and this PLU decomposition. So apart from this fundamental theorem of linear algebra business that we're going to discuss today, those 2 are going to be those 4 topics are going to be important for us for this week. And if time permits, we're going to do a review as well. Okay. Okay. And regarding the footage and releasing it, I hope to be able to release the video for this week on Wednesday, but things happen, and recently I got into color grading because someone commented on YouTube that it was like very dark, the footage, and then I realized, yeah, it is, and then now I'm trying to make it better. And another more important thing perhaps is that me and the grader, we're going to try to release the 3rd problem set grades on Wednesday as well, so that you have some time to prepare for the midterm. Okay. Now, let's first remind ourselves these 3 ideas: dimension, rank, and nullity. Rank we've been using ever since week 1, in fact, this R number that I defined. In the textbook, they define it way later, but R number. Since we learned how to row reduce, and in particular, how to count the number of pivot columns of a rectangular matrix all the way back in week 1, I took a shortcut and defined rank in terms of the number of pivots. In the textbook, they do all that song and dance, and they sort of like say, oh, this number of pivot columns is the same thing as the proper definition of the rank, which means that you can invert it and take the definition of rank to be the number of pivot columns, which we did. So just to connect everything, if you have a space of space of vectors, or if you have a subspace of a larger vector space, whatever, dimension of that space is nothing but the number of basis vectors you're going to need. Okay? Recap. Dimension of a vector space is number of vectors in any basis of V. Okay. What is perhaps slightly confusing is this idea that, or is this result that if you have finitely many vectors in one basis, then in any other basis of the same space, it turns out that you have to have the same number of vectors. So somehow, even though the same vector space might have multiple bases, they're always going to have the same number of elements, at least for our purposes. And that common number is defined as a dimension. If time permits, I'll mention a more sort of information theoretical understanding of this dimension also in a second. Rank, okay, so dimension is associated to vector spaces. Rank and nullity are associated to transformations. Okay, rank of A is the number of pivot columns of A. A transformation, a linear Alp. Okay, and nullity is the number of non-pivot columns. But then, in a sense, rank is a special case of dimension because it also turns out to be the case that the rank of A is the same thing as the dimension of its column space. So if you want, you can write it like so as well. Dim of col of A. And this is the dimension of the null space of A. Okay? And so with all this said, I can state the fundamental theorem of linear algebra. I'm going to state it, and then we're going to transition to a couple of examples. If you take these two definitions as the definitions of rank and nullity, fundamental theorem of linear algebra doesn't pretty much say anything. It sounds more mysterious if you sort of think of these spaces. Fundamental theorem of linear algebra says that rank plus nullity is equal to the dimension of the input space. I am literally saying if you take the number of pivot columns of A and add to it the number of non-pivot columns of A, you're going to get the total number of columns of A. Okay? That's why I like using these two definitions. So, fundamental theorem of linear algebra. Let's call it version 1, because we're going to update this later. Let A be a linear transformation from Rn to Rm. So it's an m by n matrix. M rows, n columns. Then rank of A plus nullity of A equals n. Okay? Which is the dimension of the input space. This turns out to be very useful. Okay? Again, like I said, if you think about dimension of column space, dimension of null space, even though these are equivalent, somehow this fundamental theorem sounds more mysterious. But if you believe in this equality and this equality, it's much more convenient to think of these, I think, at least at this stage. Okay, this is our first major statement, in fact, even though it looks so innocent. Okay. So I'll do an example specifically about this as well, but even before that, let's try to sort of connect this notion of dimension with these spaces, these types of spaces of linear spaces. I already used it here, in fact. Dimension of input space is n. So in symbols, dim of Rn then should be n. Rn should be n-dimensional. Make sense? How could one perhaps argue for this equality? How could you sort of convince someone that dimension of Rn is n? Yeah.
You need as many basis vectors as n is. So if it spans like all of R of n, then you need that many basis vectors.
Exactly. Even faster, what you can say is, look at the standard basis. 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1. OK, this is a basis, standard basis. It has n vectors in it. Therefore, the dimension is n. OK, that's how you say these kind of things in this course. So standard basis has n vectors. OK. Says any basis, which means that you can use whichever basis you want. In this case, you have a very nice basis, 1, 0, 0, whatever. So you might as well just use that. Does this make sense? How about this? What is the dimension of the space of m by n matrices? So for instance, if this was m by 1, right, this would be just the space of m-dimensional vectors. The dimension would be m.
Would it be mn then?
M times n, yeah. Again, if you want to sort of convince someone of this, well, you could say m by n's are generated by m times n many matrices. Like 1, just use 1 in one entry. You're going to need exactly m times n many matrices to generate everything. And in general, if you want to sort of leave your vector spaces sort of anonymous and consider the space of all linear transformations from V to W, this is well defined. Remember, this is a space of all linear operators from V to W, or linear transformations from V to W. In this case, the formula is the dimension of this space is the product of the dimensions. So dim of L VW is the same thing as dim V times dim W. Okay. These are three formulas that are very useful. Dimension is always going to be something I would suggest that you first sort of keep track of. Okay. Ends up being very useful in sort of eyeballing things and so on. OK. Now let's switch to another example. It's going to be about this column space and null space, really. But we'll talk about it in a second as well. I want to look at all possible 2x2s, but just the echelon forms. 2x2 reduced echelons. I want to think of each of these. There are finitely many. And I want to sort of visualize the null space and column space of each of these. Okay? We have finitely many of these, so let's separate them in terms of their R numbers. And this, okay. So we have this guy. R number is 0. If R number is 1, reduced echelon form is either this or this. Okay? And if R number is 2, then that means that the reduced echelon form has to be the identity. These are all possible reduced echelons in the case of 2 by 2. Okay? Now I'm going to think of these as transformations from R2 to R2. What was the column space of a linear transformation? I should ask you. What is the column space? You should know this for the exam. Someone else. Someone who hasn't spoken so far. What is the column space of a linear transformation? You're cooked if you don't know this, okay?
Whatever shape it makes, it's the space that it follows? Is that it, or?
Oh, you need to massage that a little bit, yes?
It's close.
What is the column space of a transformation? Not you, someone else. You speak also. Say again? Span of columns. Column space is literally the space of columns, which means it's a span of columns, okay? You need to know this. So column space of A is the same thing as the span of columns of A. Take all columns of A, you look at their span. Okay? So, in this case, so column space is always going to be a subspace of the output space, okay? So even though in this case, because these are 2 by 2s, they all go from R2 to R2, column space you want to always think of in the output. Okay? Column space, well, first column is 0, 0. Second column is also 0, 0. What is the span of 0, 0? It's just a 0 vector. So the column space is just the 0 vector. Okay? Make sense? What is the column space of this? You need to look at the columns. This? Okay. 0, 0, okay, you don't need to care about that. 1, 0 is the horizontal vector, so you just get the x-axis. You see, this is a subspace of the two-dimensional space. That's an example. Column space is a subspace. How about this case? What is the column space? Same thing. Okay, so there's a star here. It could be 0, it could be non-zero. I don't really care though, because this already gives me horizontal motion. This is not going to contribute anything. Just because you're looking at the span of columns, you don't need to worry about linear independence, okay? Span is a different thing. Maybe you have redundancies. I don't care. Same thing. How about this? Yeah.
Can you explain why it's horizontal one more I thought you said like the left side was like theoretically the x coordinate, or are
What
we
do-
talking about
What do you mean?
like the left side, like 0, 0 is like represents x, and like the 1, 0 represents y?
No, you're mistaking it with something else. The other thing is this, okay? 0, 0 is where this matrix takes 1, 0 here, 2.
Okay, I see.
Okay?
Okay, I get it, yeah.
So 1, 0 being in the second column really represents the fact that this transformation takes the vertical input, transforms it into a horizontal input. Very good. So let me draw this better. What is the column space of identity? Everything. What is the span of 1, 0, and 0, 1? Well, 1, 0, and 0, 1 is a standard basis of the plane. So it has to be everything. Okay? It's everything. Okay? What is the null space of a transformation then? What's the definition? Let's remind ourselves. This is more complicated than column space. But let's, I'll wait for you to think a little bit. Maybe look at your notes. Yeah, go ahead.
Doesn't it deal with redundancy of vectors in the sense that, for example, looking at the echelon forms for 1 or even 0, we have a redundancy in the 1, 0, star 0 of the star existing, so that would, in a sense, be the null space?
Yes. But maybe I'm looking for something shorter.
Okay.
Fast, yes.
The span of the redundant vectors in the original set,
If you were forbidden to use the word redundant.
the linearly dependent ones.
That's okay. Good. The formal definition, or the, how to say, official definition is the set of all solutions of AX equals 0. All x's, x is a vector in the input, that A transforms to 0. I like this more because it's like a more transformational one. But you're all right, ultimately. So for instance, here, if I were to take this as A, and if I were to try to solve AX equals 0, well, no matter what input I plug in, it's going to be 0. So the null space of this is everything. Make sense? What is the null space of this guy?
Anywhere in the y direction.
Very good. Well, I mean, say again?
Would it specifically just be the y-axis?
Let me think. Okay. Let's be a little careful. I take this as my A. Say I'm trying to solve x1, x2 equals 0, 0. Okay? It's kind of backwards, but this would require that x2 is 0. Right? When you multiply this side is x2, 0. Right-hand side is 0, 0. So x1, x2 would solve ax equals 0 if and only if the second component is 0. It's kind of the other way around. And that's why null space is more confusing, I think. So what does it mean for x2 to be 0? Well, that means that x1, x2 has to be horizontal. So the null space of this is, again, this. Okay. That's also one of the reasons why it's good to separate input and output. In this case, null space and column space ended up being the same, but that is not in general true. Okay? Okay, how about the null space of this guy? Any guesses?
Be like nothing, zero vector. Just what you're saying on with the last one.
Okay, so that cannot be true, first of all. And here's the heuristic. This is where you can use the fundamental theorem of linear algebra. You know the input dimension is 2. You know the column space is one-dimensional, so the rank is 1. So null space has to be one-dimensional. So null space is a line here, actually. You don't know where it is exactly, how it looks like, but it has to be a one-dimensional thing. This is the benefit of the fundamental theorem. Even before computing anything, purely by the fact that this has R number 1, you know that it has a null space, in fact. Okay. Does that kind of make sense? This is the main use of the fundamental theorem of linear algebra.
If that's the case, why is your previous logic incorrect?
What do you mean?
Or because what he was saying and what made sense to me is if so that star could be any positive integer, correct?
Yes?
So if we had 1, 0, 1, 0, for example, then both x1 and x2 would have to be 0. In which case,
No, no, no.
no?
No. Good. That's why this example is good. So already you see, already at the reduced echelon forms, this is like getting complicated. I told you, null space is harder to make sense of. Column space is easier. I just open up the definition. And this is also why this redundancy business and stuff for null space is going to get confusing. That's why it's, as far as I'm concerned, AX equals 0, the system thing is the best way to think about null space, at least at this stage. Okay, so I take that guy. And because instead of star, I'll just use some number, b, some letter. Okay. And I'm going to try to solve a x1, x2 equals 0, 0. Now, b could be 0, and it could be non-zero. But in any event, if I do this multiplication, what do I get? x1 plus b x2 in the first entry, and then 0 in the second entry. And I want this to be 0. Which means that I want x1 plus b x2 to be 0. Now this is the equation of a line in the x1, x2 plane. Okay? Now I cannot, at this stage, solve for x2 because I don't know if b is 0 or not, but I can think of it, I can solve for x1, and I can write it as x1 equals minus bx2. So I'll write it here. Okay. And here's what you can do. Instead of saying, oh, x1 is the horizontal, you can just change the labels. Say horizontal is x2 and vertical is x1. Now minus b is my slope. Okay? Whatever this line is, right? So if b is 0, it is horizontal. If b is a positive number, it is like this. If b is a negative number, it is like this. I'll just draw like a typical picture, maybe something like this. That's my null space. Depending on B. Does this make sense? Okay. Null space is harder. Any comments or questions about this so far? Yes?
Why can't we just switch the variables? Wouldn't we have to call it like 1 over b? Or?
Well, I mean, instead of, well, I can literally just take this board and flip it like this and look at it like that too. Okay. Right? It doesn't matter. Yeah. Yes. That's why I can do it. It's just easier for me to visualize this in the x2, x1 plane as opposed to x1, x2 plane. Because in the x1, x2 plane, minus b is not the slope. Yeah, this is x2.
It just looks like a B, so. That's the red one.
Okay? So, okay. Slope minus b. Okay. Comments, questions about this so far? How about the final case? What is a null space?
There is none?
Exactly. Two-dimensional fundamental theorem of linear algebra says if this is 2, this has to be 0. Okay? Comments or questions about these so far? Okay. Now, here's the complication. When you apply, if you start with an arbitrary matrix, to figure out the rank and nullity, or at least one of them, you're going to have to do some, typically, you're going to have to do some row reductions, okay? Because if I were to sort of change things and so on in like 3 by 5, whatever, it wouldn't be in general that clear which ones are the pivot columns. So you're going to have to do some row reductions. But the catch is, if you do row reductions, maybe the column space and null space are going to change. Rank and nullity are not going to change, these numbers. Okay? But the positions of the null space or the column space might change. Here's an example, for instance. I'll do a more complicated example in a second. But even in the case of 2 by 2s, this becomes apparent. Say A is 1, 0, 1, 0. Okay? It's clear in this case. It's not that complicated, but it'll be good. Now, before doing any row reduction, okay, if I were to ask you, what is the column space of this guy? What would you say?
Would it be like the XY, or yeah, the X?
Diagonal, yeah. So this time, you see, this doesn't do anything, but the first vector, first column gives you the diagonal. Okay? So now the column space is y equals x. Null space, by the fundamental theorem of linear algebra, is also one-dimensional. What is it?
Would it be x2?
What do you mean x2?
Like the second column?
You can't think of the null space in terms of columns like that. You have to set up the system. Set up ax equals 0, and solve it. Okay, that's the fastest and surest way of determining the null space. Yeah.
X1 would be set at 0, and then x2 is free, so it's vertical.
Yeah. Well, I guess you were right then. That's what you said too, right?
Yeah.
Okay, yeah, okay, fair enough. So I got confused, I guess. So just to reiterate, take the matrix, set it to 0, x1, x2 is 0, 0. What does it say? X1 x1 and x1, yes. Thank you. But this is x1 times 1, 1. Well, this is a non-zero vector. You know, the only way this can happen is if x1 is 0. Which means this has to be a horizontal guy. Sorry, the vertical guy. x2 is free, so this is null space. Yeah, for some reason I was thinking the other diagonal is the null space here. But yeah, you guys are right. Okay. Any comments or questions about this so far? But you see what happens when I do row reduction. Because now, suppose I wasn't able to see all this stuff. Delete all this. Say this is like a more complicated matrix or something. I do row reduction. But of course, if I were to do row reduction, I would just subtract the first row from the second one, and I would turn this into 1, 0, 0, 0. So you see, well, I'll just do it here. Let's call this new matrix maybe A bar. It's not quite A, it's a different matrix. This is my A matrix. Here's A bar. The column space and null space of this, we figured out over there. Well, the column space of A bar is horizontal. And the null space of A bar, B is 0 in this case, so x1 is 0. That's going to be horizontal also. Yeah. Hang on. Well, in this other picture. It's null of. Okay. Which is the same picture as this. This matrix is not A bar, but you know, they might have the same thing. Okay. So now you see that's the complication. Null space, or rather column spaces are different, and so are the null spaces. Yeah.
The null space is still the same, right? The only reason it looks different is because you have the different axes.
Is it?
It's still set to 0, so it's still like if you're setting the same axis.
Yeah, I guess I shouldn't have moved these variables that much. So if this is x1, this is x2. We said x1 is 0. In this case, if this is x1 and if this is x2, x1 is 0 again. So yeah, you're right. In this case, the null space is the same. It might even be the case that null space always stays, but let's not worry about that. What does matter is that at the very least, column spaces are different. Okay. I might be wrong in that row operations maybe keep the null space. I would need to think about it. Let's not worry about it. You should just know that when you do row reduction, column space or null space in general might get mixed up. Their dimensions are going to stay the same. Okay? One dimension, one dimension, one dimension, one dimension. But the specific positionality, the specific way in which these column spaces are configured inside a larger space might change. That's the main complication regarding these matters. So, in a more complicated example, how do you handle this situation? Here's the more complicated example. I'm not going to do the row reduction explicitly. I'm just going to give you the reduced form of the matrix also. So, it's an example from the textbook. Say you have the following 3 by 5. -1, 2, 5, 1, 3, 8, -7, -1, -4. This is a 3 by 5. So it goes from R5 to R3. 5 dimensions to 3 dimensions. Just write it like this. Now, even before doing anything, I look at the input dimension, in other words, the number of columns, that's 5. I know that rank plus nullity is going to equal to 5 by the fundamental theorem. Okay? And of course, these are at least 0. So you have 5 different options or 6 different options. And so this could be 0, 1, 2, 3, 4, 5. And this is going to be 5 minus whatever the rank is. Now, at this stage, it's not super clear what these numbers are. So now you need to do row reduction. Say you do it successfully, and you end up with this matrix. Let me call this U. So maybe like this. A turns into U, and this new U matrix is this. 1, minus 2, well, 1, 0, 0, minus 2, 0, 0, 0, 1, 0, minus 1, 2, 0, 3, minus 2, 0. You did your row reduction, and you ended up with this. Indeed, this is in reduced form. Here's my staircase. What is the rank? 2. Why? Because there are 2 stairs. Rank is 2. Same thing as the number of pivot columns. Rank is 2. What is the nullity? 3. 5 minus 2 is 3. Okay. So, there's Pivot columns are the first and the third columns. Nullity is 3. 5 minus 2 is 3. Non-pivot columns are column 2, 4, and 5. Okay. Now I want to figure out the column space of A and null space of A. Okay. I know at this stage that the column space is going to be two-dimensional and the null space is going to be three-dimensional. Meaning, column space is going to be a plane inside this three-dimensional space, and null space is going to be a three-dimensional space in this five-dimensional space. Okay. Just because you got this reduced form, you don't get to say that the column space of A is the xy plane inside 3 dimensions. You don't get to say that. Okay? I'm not asking for the column space of U. I'm asking for the column space of A. And again, you don't get to look at just the null space of this U matrix and associate that to the null space of A. All you know is the dimensionalities. I'll write that too. So all you know is that the column space of A is two-dimensional and the null space of A is three-dimensional. Okay. Now, to really visualize the column space of A and null space of A, well, you would need to display a basis for the column space of A and another basis for the null space of A. So, need a basis for col A. Again, you cannot just say 1, 0, 0, and 0, 1, 0. That's not going to work in general. And you need a basis for null space of A. Again, we figured out how to extract a basis for the null space of a reduced form matrix, but we're going to have to be worried about how to do that in general. Just by this fact, that rank is 2 and nullity is 3, I know that for column space, that means I need 2 linearly independent vectors. And for null space, I need 3 linearly independent vectors. I don't know what they are, but I know how many I need. Okay? So, two vectors. 2 vectors that are linearly independent. For this, we need 3 vectors. Nullity is 3. Null space basis has 3 vectors. I don't know what they are at this stage. I know I'm going to need exactly 3. And again, I need these to be linearly independent. Okay. We still have some more work to do with this example, but this is a very important example that I want to spend some more time on tomorrow. Okay, that'll be it for today. Thank you. Anyway, okay, let's start. Good morning. So, we have a couple of things to do. We have a couple items to discuss. Block matrices, or in other words, partition matrices and affine transformations, I'm going to leave to tomorrow. And today, we're going to work on this example that we started with I decided to sort of incorporate some sort of a review in this as well. Yesterday I gave you, oh, here's a matrix and here's the reduced form of it, but we might as well sort of take our time, do this row reduction once more. And then using this row reduction, I'm going to introduce these elementary matrices as well. Now, before that, I said something wrong. I said when you do row reduction, you might break the null space. That is false. I made a mistake, OK? When you do row reduction, null space is going to be preserved also. So what does this mean? It means you start with an A, do a bunch of row operations, and you end up with some other matrix U. Maybe it is echelon, whatever. Rank of this and the rank of this are going to be the same, the numbers. Nullity of this are going to be the same. Furthermore, the null space of this and the null space of this are going to be the same also. The only thing that row reduction might break is the column space. The column space of A need not be the same thing as the column space of U. Okay? Null spaces, fine. Rank and nullity, these dimensions, integers, they're certainly fine. Column space might break. Okay, just wanted to clarify and correct myself. There are other situations where instead of doing row reduction, you do column reduction, in which case null space might also be broken. So, yeah. Okay, so here's the example that we started talking about yesterday. This is a 3 by 5. And in fact, I'll mention something too. Here's my matrix. I'm going to try to write everything nicely. -1, -3, 1, 2, 6, -2, -4, -1, 2, 5, 1, 3, 8, -7, -1, -4. Okay. And what is this example about? Well, say everything you can say about this matrix at this stage. So what is the rank? What is the nullity? What is a basis for the null space? What is a basis for the column space? These kind of things you should be able to answer. So what is rank of A? Nullity of A. Basis for column space of A. Basis for null space of A. At least at this stage, you should be able to answer these 4 questions. What is A basis? Okay. Now, even before that, one of your colleagues at the end of last class asked me a question, namely, well, I guess the issue was a little bit about this interpretation of this 3 by 5 as a linear transformation. Your colleague today is not here. Yeah. But we've been saying so far, whenever you see a matrix, okay, you need to immediately take note of the 2 integers that are the number of rows and the number of columns. In this case, this is a 3 by 5, okay? And we write them like so. Row number goes on this side, column number goes on this side. Whenever you have a 3 by 5, I said you can think of it as a linear transformation from R5 to R3. Okay? So I'll write it here with more words. So A is 3 by 5, so one can think of it as a linear transformation, linear operator, linear op, from 5D to 3D, so R5 to R3. So what is a linear operator? To begin with, it's a function, okay? So if you want to think of this A as a function, you think of it as something that you feed a 5 tuple in. It's a function that depends on 5 variables, and it gives you 3 outputs, 3 scalars, as a function of these 5 variables. So here's the complicating part, I think, if I remember correctly, what your colleague was suggesting. Somehow, to say something about this specific linear transformation, where I am sort of inclined to think of this as one thing, even though it has a bunch of components, well, I look at something like the column space, meaning I just single out each of these columns, and these are 3-dimensional vectors, which means that they're all in the output space, and I do something with them. I look at the basis, linear independence, whatever. But somehow, how do you connect? Well, separating each of these vectors and how they are positioned inside the output space to A as a linear transformation. Well, we had talked about this a couple times before, but I think it's worth saying. In transformation notation, for instance, I would write this A, one way of writing it like this. Okay. It's a function that takes 5 inputs, okay? And what is this output? Well,
Good morning.
morning.
I cleaned the whiteboard.
Thank you.
You're welcome. Tomorrow is Wednesday, everybody.
Yeah. So this tuple, at this point we know, we can also write as a 5 by 1. And what does this mean? Well, these are all scalars. A of that means, well, take each of these columns, scale each of them.
Valentine's Day and President's Day, everybody.
That's true.
Valentine's Day and President's Day. Have a good day, everybody.
Yeah, thank you. So you take these 5 numbers, and each of them you use as a scalar for each of these columns. So ultimately, when you plug in x1 to x5 into A as a function, the output is going to be the associated linear combination of these columns. Okay? So this is x1 times this. I'll just write it explicitly. x3 minus 1 to 5 plus x4 1 3 8 plus x5 minus 7 minus 1 minus 4. Okay? So in a sense, taking a bunch of column vectors like this and assembling them into one matrix represents this idea that, well, I have a bunch of motions in different directions, and somehow when you put all of them together into one matrix, you want to sort of, you're combining in a linear fashion each of these motions in different directions. Okay? And so for instance, if I were to plug in 1, 0, 0, 0, 0, well, this is just going to be 1, and all others are going to be 0, which means that A of 1, 0, 0, 0, 0 is going to be nothing but the first column. Why? Because when you plug in 1, 0, 0, 0, 0, A behaves in a somewhat pure fashion. It says, oh, I'm just going to look at the first column, and that's my motion. That's what it says. Okay? But if you plug in 1/2, 1/2, for instance, so 1/2, 1/2, 0, 0, 0, you're saying under A, use the first motion 1/2 units, and then the second motion 1/2 units. Because of linearity and the fact that it doesn't matter in which we write these additions, it actually doesn't matter which one you use first. In the nonlinear situations, it does end up mattering, but we're not going to be worried about that. But so that's sort of like one way to perhaps connect the transformation idea to the linear combinations and spans and stuff. Does this kind of make sense? I don't know. I'm just waxing philosophical here a little bit, perhaps.
This is going to be a silly question.
Yes.
That's different than matrix multiplication, right?
What do you mean by that?
Is that
You mean this?
Is that just matrix multiplication?
Yes. The complexity of this course, of this class, is all about, well, there's one idea, and we have like 75 different ways of writing the same thing. And, 100 different ways of calling the same thing. It's like they have like different names. But yeah, it's like if I wanted, in more standard notation, I would just write it, or in matrix multiplication notation, I would just write it as this: A times x1, x2, x3, x4, x5. The same thing.
And we normally just abbreviate it AX, correct? As well.
Yeah, and then you would sort of even go further, and you would just package it into one x. You're right. Does that kind of make sense? Well, here's a riddle, okay? Perhaps I should have said this earlier, or pointed this out earlier. Well, what if I were to take one of these columns? Let's say I take the middle column. Okay? This is a vector. It's a vector in R3, but it's also a 3×1 matrix, which means, just like in this case, that should represent a linear transformation from R1 to R3. Linear operator from R1 to R3. Remember I told you how this is like all like some narrative. So vector is the same thing as matrix, same thing as linear transformation. They're all the same things in a sense. But what could that mean, you see? If you were to take a vector in R3, it's the same thing as, I'm telling you, as specifying a linear transformation from R to R3. And how does this work? Well, matrix multiplication is supposed to work, right? And so, well, this is 3×1. I can only feed to it a 1×1, so a constant, a scalar. Let's say t. That's a 1×1 for matrix algebra to work, right? So when you put two matrices next to each other, the middle dimension has to match. And when you do this multiplication, you're going to end up with a 3×1. And of course, in this case, there's nothing much to do, but you have 3 rows on the left and 1 column on the right. When you do this matrix multiplication, you get this: minus t, 2t, 5t, which of course is nothing but scalar multiplying this vector by t. But the interpretation is different in that I'm taking this now as a linear transformation acting on one-dimensional space. It's kind of confusing. But if I'm trying to visualize this or imagine this 3 by 1 as a linear transformation, consequently from R to R3, how can I visualize this? Well, if you have a 3 by 1 as a linear transformation, what it does is this. It takes an abstract R1, let's say. I'm sort of imagining this R to be sort of living in the ether. Okay, this is like some abstract copy. Okay, this specific transformation takes this abstract R that lives within nothingness, let's say, and puts it into this R3 in a very specific fashion. It says, oh, there's this abstract R, put it into this R3 so that it points to, so -1 is somewhere here, 2 is here, 5 is there. Okay. Take that arrow, and now take this, the abstract R, and turn it into this very specific directed line in 3 dimensions. So this is abstract line, and turn it into the line that is a span of -1 to 5. Okay. So somehow all of these interpretations are compatible. If you have one column, it tells you what to do with an abstract line and how to position it in the output space. Well, if you have 2 of them, it tells you how to position a plane and so on. That's another way of imagining the same thing. Did this kind of help at all, or maybe got you more confused? I don't know. Comments or questions about any of this? Yeah.
So the 3 by 1 vector is the transformation, right, onto T?
Yeah. Yeah. Yeah, so somehow the way I imagine it is, insofar as matrix algebra allows me to write something down, it has a meaning. That's how I sort of think about it. Any other questions or comments about this? Okay. So, I'll erase this. So there are multiple ways of sort of interpreting what is happening. It's good practice to start telling yourself some stories, and these notions of rank, nullity, and so on, and even column space, null space, all these things, you can imagine them to be sort of tools to help you build your own stories about what is actually happening. Because somehow, us humans, so for us humans, something like this as sort of like an array of numbers doesn't really mean much. It's just a bunch of numbers. So you want to come up with a story. Okay. So first, let me finish up what I was saying, and then I'm going to expand on this row reduction again. Just going to say, for now, let's take for granted that the reduced echelon form of A is the following. I'll say row reduced if you want to be more explicit. Is U. And I'll add U here. Okay. I want to keep it 1, 0, 0, minus 2, 0, 0, 0, 1, 0, minus 1, 2, 0, and then minus 7, minus 1, minus 4. Okay. For this part of the example, I'm just going to take this row reduction to be true. In a second, once we're done with answering these questions, we're going to go back and actually do this row reduction as well, just to remind ourselves. Whenever I see something like this, what do I want? I want this staircase pattern. And how is the staircase defined? There's a minus 4 there, so I guess, oh, because that is the last column of A. Sorry. So that should be 3 minus 2, 0. Okay. So I have this staircase pattern. It starts from the top left, ends up at the bottom right, and I'm always going down. Underneath my staircase, I want to see all zeros. Above the staircase, I don't want to, I don't really care that much, but the stairs, rather the steps, are always at these pivots. Now, rank of U is the same thing as the rank of A. Rank of A, same thing as rank of U. And what is the rank of something like this? Well, it's the number of pivot columns. In this case, I have 2 pivot columns, two stairs. So this is 2. Nullity of A is the same thing as the nullity of U. And that is exactly the number of remaining columns, non-pivot columns. I had done this yesterday, but I'm taking it slow and repeating. And so how can we compute this? We can say, oh, either one of these is 3 by 5. They have 5 columns. Fundamental theorem of linear algebra says these two have to add up to the total number of columns. So this is going to be 5 minus 2. 5 minus 2 equals 3. Okay. Question?
Yeah, so it's about the note. Yesterday that I wrote, we have nullity, rank of nullity is 3, but why is it equal to today?
Rank of nullity?
Yeah.
You don't want to say rank of nullity. That doesn't really mean much.
Oh, how about the dimension of nullity of matrix A?
Dimension of the null space of A. Yes, okay. Dimension of the null space is the same thing as the nullity. You're right. That is true. And that's what I was going to say in a second. So just like the first thing we do when it comes to matrices is figuring out the number of rows and columns, I would suggest computing the rank and nullity of something is also something that you should keep track of. Because somehow rank is related to column space, nullity is related to null space, but in general, null space and column space, these are subspaces, these are vector spaces. So you're going to have to compute some bases, whatever. These are more complicated. Rank and nullity, you want to think of them as proxies. Proxies as to how complicated these spaces are. Right? So, for instance, the fact that this number is 2, the rank is 2, tells me that, well, column space is going to be two-dimensional. It's going to be a plane. In a sense, for instance, this 3 tells me that the null space is going to be three-dimensional, and because of that, null space is more complicated than column space in this case. That's sort of like a heuristic you can think of. Because, imagine calling someone, oh, that person is very one-dimensional. Probably that person is like very simple, right? Not much to do. Or, that character. Or, you would say, oh, in this film, it's like this character was very three-dimensional and blah, blah, blah. More realistic. The higher the dimension, the more complicated things are. Okay? Any questions so far? Now, once you're here, you say, well, rank of a matrix is the same thing as the dimension of its column space. And what is the dimension of whatever? Well, it's the number of vectors any basis of that space is going to have. So, any basis, I'll remind you what this means also, of column space of A as well as the column space of U, because the rank of both of these are both 2, as well as of column space of U has to contain exactly 2 vectors. Okay. So this 2 is the same 2 as this 2. Okay. What else can we say? Because both of these matrices are 3 by 5, okay, columns are three-dimensional, meaning these vectors that you need to find are going to be three-dimensional vectors. So I can just say exactly 2 vectors in R3. Okay. So this 3 is not this 3, okay? This 3 is this 3. It's a number of columns, number of rows. Any basis, on the other hand, of the null space of U, which I'm telling you is the same thing as the null space of A, is going to contain 3 vectors, but this time in R5. Any basis of null space of A, which is the same thing as the null space of U, has to contain exactly 3 vectors in R5. This 3, number of vectors in the basis, is the same thing as this 3. Okay? Running out of colors. Just do this. This 5 is the same 5 as this 5. Any questions so far? Now, what do I mean by a basis? Well, basis is going to be a set of vectors that satisfy certain things. For a basis of the column space, I would need two vectors, exactly two vectors, in the column space of A that both span every other vector in the column space. So the span of these two vectors, I want to be the whole column space. And furthermore, I want these two vectors to be linearly independent. In the case of two vectors, you can just imagine linear independence to be, well, they should be pointing to different directions. Okay? And likewise, in the case of a basis for the null space of A, this time I need three vectors in R5 that happen to be in the null space of A that are linearly independent, okay? No relation between them. And they span the whole thing. So I'll just add here, basis means linearly independent and spanning. Recall so basis of a subspace let's call it W, is a set of vectors in W vectors in W that are linearly independent, so there's no linear relation between them. That is linearly independent. Li, and that spans the whole W. It's a little trick that for the types of vector spaces we're looking into, if you have linear independence, oh, I'm not going to finish it, sorry. There's a situation where you can sort of fast forward this as well, but let's not get into that. So that's what we need. We computed rank and nullity. Rank of A is 2. Nullity of A is 3. But we need to figure out a basis for the column space and a basis for the null space. Okay? Any comments so far? So, null space of A, let's first figure that out, is the same thing as the null space of U. And so, to figure out a basis for the null space of U, well, I'm just going to set Ux to be 0. So basis for null space of U, null space of A. This is the same thing as null space of U. Set Ux equals 0, and now you solve it. The point of having this reduced form, which I guess I'm not going to be able to, I may not be able to finish reducing today, but never mind. You set this, and given that this is already in reduced form, you just open up and write down the general solution. Okay? And so x, which is going to be of the form x1 to x5, So for instance, the first row of u tells me that instead of x1, I can write it in terms of the other variables. Specifically, this is going to be 2x2 plus x4 minus 3x5. x2, I don't get to say anything about it. It's a free variable, so I'm going to leave it as is. x3, however, I can write in terms of the other ones. Minus 2x4 plus 2x5. And then I don't have anything about x4 or x5. I don't have anything about x4. I don't have anything about x5. So I'm just going to leave them as is. So in the system notation, x2, x4, and x5 were the free variables. I'm just not doing anything with them. The other ones, I write in terms of these free variables. That's the method I'm using here. But the point of doing this is that once you have something like this, you can split everything. Okay? You think of x2, x4, and x5, the free variables, to be the scalars, and you sort of write this as a linear combination. x2 times 2, 1, 0, 0, 0, plus x4 times 1, 0, minus 2, 1, 0, plus x5 times minus 3, 0, 2, 0, 1. Okay? Any questions about this? This is this vector addition, whatever.
Where are you getting the 2x2 plus x4 minus 3x5?
So when you open this up, the first row is going to tell you x1 minus 2x2 minus x4 plus 3x5 equals 0.
Okay.
Solve for x1. Says x1 is this. So instead of writing the difference between these two is 0, I just solve for x1.
Okay. Yeah.
Make sense? Yeah. So I solve the variables that correspond to the pivot columns, so 1 and 3, in terms of the free variables to get this expression. Okay? Any other comments or questions about this? What does this say? A 5-dimensional vector x is in the null space of A if and only if it is a linear combination of these 3 vectors. But then, for instance, I can immediately conclude that these 3 vectors have to be a basis for the null space. Because look, there is no redundancy between them. Only the first vector allows me to move in the second direction. Only the second vector allows me to move in the fourth direction. And only the third vector allows me to move in the fifth direction. So they have to be linearly independent. Okay? Which means these 3 5-dimensional vectors both span the null space and they are linearly independent. In other words, these 3 vectors is a basis for the null space. Okay, so it's the basis for the null space of A, which is the same thing as the null space of U. This is 2, 1, 0, 0, 0. That's the first vector. Second vector is 1, 0, minus 2, 1, 0. And then the third one is minus 3, 0, 2, 0, 1. And if you want, you can use this set notation. Okay. Already at this stage, I knew that I'm going to need exactly three vectors for the null space. But now I was able to compute explicitly three vectors that are in the null space. And as usual, just to verify, what you can do is you can take any one of these vectors, multiply it with A. You should get the three-dimensional zero vector, for instance. Okay? Well, for instance, let's just check the first vector, 2, 1, 0, 0, 0. Take that, multiply it by this. You should get 0. Why? Because when you do this matrix-matrix multiplication, well, what does that correspond to? It says take the first column, multiply it by 2, and add it to the second column. All that is certainly true. If you multiply this by 2, minus 6, 2, minus 4, minus 6, 2, 4, add it to this, you're going to get 0. Does that make sense? I see a lot of confused faces.
I can see why it's true. I see that it is true, but I don't know why it has to be true.
What do you mean?
Meaning, if I do that, obviously if I multiply, I can see what you're doing and why it's true, but I don't understand why that must be the case.
So I guess you're saying maybe there's some other example where this may not work. Fair enough. Just take my word for it. In this class, I think it's good to just focus on the method and that it works. Yeah, it will work every single time. Yeah. In a second, once I switch over to these elementary matrices, I'm going to try to make more sense out of this. Well, okay, I did some calculations, and I'll just try to convince you this way. Okay, let me try to find this. Okay. Exactly. So this is going to look like magic, but this is what I was hoping to spend more time on. Why this ultimately works has to do with this factorization that is underneath. Somehow, the fact that U can be obtained from A using finitely many elementary row operations correspond to the fact that A factorizes. Let's say B U. A is that A, U is this U. So if this is 3 by 5, and this also is 3 by 5, it means that B is 3 by 3. And it's an invertible matrix. And I did some calculations, and looks like magic for now, but I somehow came up with this specific matrix B. And you can do this multiplication to verify. Okay. Okay. Somehow, if you use this specific 3 by 3, this equation is satisfied. And somehow, it is also the case that this is invertible. I also know this for whatever reason. Ultimately, because you should imagine this B as, well, a packaging of all the row operations you're going to use to go from A to U. every single row operation ultimately is going to be an invertible matrix, which means that their product, which I am just telling you, and I want you to take for granted for now, end up being this B matrix. Well, their product too is going to be invertible, which means that this equation can be written as BUX 0, but then B is invertible, which means that I can send it to the other side. But then B inverse is a linear transformation, and in a linear transformation takes 0 to 0 vector. And so the null space of A has to be the same thing as the null space of U. All I need to do then is to figure out, all I need to do is to focus on the null space of U. Does that kind of help maybe a little bit? This came from here. Yeah.
So we did the basis for the null of A. What's the basis for the column of A?
Yeah, we haven't done that yet.
Okay,
That's true. But I guess I'm running out of time. Just to answer your question. So we handled these three, okay? We need to figure out the column space of A. Now, with the column space, even though it is easier to compute, okay, you just look at the span of columns compared to the null space as far as I'm concerned. The column space might be different for A and U. So the column space of U is, well, it's the xy plane in the three-dimensional space. To figure out a basis for the column space of A, what you do is you mark the pivot columns in U, you go back and look at the same columns in A. This is perhaps more surprising, but then it turns out that the basis of the column space of A is the span of these two. Yeah.
Since we're looking for two-dimensional plane,
Yes.
couldn't we take any two columns that are linearly independent,
Yes.
and those would be a span?
Yes.
So it's not necessary that we take those two columns.
Sure, but like this is something like an algorithmic almost.
Okay.
Yeah, you're right. You can take any two columns that are linearly independent, but tell me two of them.
I guess those two are.
Yeah, like those are the most obvious choices in a sense. So like if you're taking the first one, you're not going to take the second one. But of course, instead of taking the first one, you can take the second one too, because these two are proportional, the first and second columns. Sure, there's no unique choice of a basis. There are multiple bases. All you need is one. Yeah. Okay, I'm out of time. I'm going to say even more things about this tomorrow. I think this is a nice review, but that's it for today. Thank you. All right, let's start. Good morning. So my initial plan was to discuss elementary matrices and this block matrices and affine stuff by the end of this week as well. But you guys weren't as enthusiastic as I would have liked you to be. So I'm postponing this blocking stuff and the affine stuff to next Monday. Today we're just going to focus on this example that we've been dealing with. I'm just going to introduce these elementary matrices. I'm also not going to go too much into detail about these LU factorizations. So we'll just spend today completing our discussion about everything about this. I also wanted to ask you if you have any special requests regarding review topics for the midterm. I'll be able to sort of fold whatever you would ask into this example, I think. Yeah, while you're thinking about what you would perhaps want reviewed, I'm also taking attendance. Okay. Any requests regarding review topics and stuff? Yeah.
Can you do something like number 5 on problem set 1 where you just give us a vector and it's like find the rank, the nullity, the determinant, trace, kind of what you did in class with the span?
Well, I mean, we're doing rank nullity and stuff in this example to begin with.
Can you do another example like that one?
Sure, I'll do another example. Another one. So I guess I'll write it here. Another example of rank nullity stuff. What else? Here's a slightly fancier example for this. We had talked about traceless matrices. So let's call this W, A, B, C, D, such that A plus D equals 0. This is a subspace of the space of 2 by 2s. We had done this example before. I'm just going to fast forward the parts that we have already discussed. We realized bases, one basis for this is 1, minus 1, 0, 0, and then 0, 1, 0, 0, 0, 0, 1, 0. It's a basis, which means that its dimension is 3. Okay, we have done this example before. I'm just reiterating. In a sense, we can sort of think of this in terms of rank nullity as well. I didn't say this at the time, but you can think of W as a null space of some linear transformation. Namely, the transformation that takes A, B, C, D and gives you back A plus D is a linear transformation, which is the trace. So T goes from 2 by 2s into reals, one dimension. So T of A, B, C, D is A plus D. That's a function. It's a linear transformation. Well, its rank of T is everything because, so T of T 0, 0, 0 would be just T. So rank of T is 1. Well, rank nullity says rank plus nullity has to equal to the space of inputs. In this case, this has dimension 4. And so I can just conclude that even before looking at the basis of this whatever, then W is the same thing as the null space of T, where T is 0. And nullity of T would be the same thing as the dimension of W, which is 3, which has to be dimension of this, which is 4 minus 1. That's another example of using this rank nullity business. So in fact, just by looking at this expression, W is the subspace of 2 by 2 such that A plus D equals 0, you could have deduced that you're going to need exactly 3 2x2s to come up with a basis for W. This is like a highbrow example of this rank-nullity. I'll do a more conventional example in a second. Any other sort of suggestions regarding review topics? Yeah.
So the last example, you had us find like what is the rank nullity basis for column of A and like basis for nullity of A. Do you like that one right there?
Yeah.
Do you have? I don't know if we're used to coming up with those equations yet. So can we have a practice for coming up with like the basis for the nullity of A and the basis for the columns of A?
Oh, okay, sure. Yeah.
Yeah, because you're like finding out which x's are like free variables. I don't think we're used to coming up with those equations yet.
Let me think. So I guess we can look at this one. It's a practice problem. This is a 3x3. Let's just fast forward the row reduction parts, and I'm going to give you the echelon form of it. Okay, A is 1, 2, minus 3, minus 1, 0, minus 5, and then 5, 7, minus 3. And then you do row reduction, and you get the form 1, 0, 0, minus 1, 2, 0, and then 5, minus 3, 0. Let's just take this for granted. You can keep simplifying this a little bit further if you wanted, but this is already in echelon form. It's not reduced, it's echelon. So the question is, what is the rank nullity basis for column space, basis for null space for either one of these matrices? I'll write these down. So basis, A basis for column space, of A basis for null space of A, then rank of U, rank of A, nullity of U, A basis for column space of U, A basis for null space of U. Now, in practice, you wouldn't receive this reduced form. I'm just fast forwarding here so that we can just focus on these notions. Yeah, just take a couple minutes to try to answer. Some of them you should be able to answer immediately by looking at, say, U. Okay, so let's start. What is rank of A? Two. More, less? You just look at the number of pivots, okay? Doesn't matter. You can just look at this guy. So the integers are going to match. Null spaces are going to match also, but column spaces are going to be different in principle. And so you look at the number of pivots, 2 steps, 2. 2 steps, 2. Rank plus nullity is the number of columns. Well, I should have maybe not said that. So what is nullity? 1, right? Because 3 columns, if you have 2 pivots, 1 non-pivot, nullity is 1. Okay? Rank is the same thing as the number of vectors in the basis for column space. So for a basis of column space, I'm going to need 2 vectors. Okay? Likewise here, I'm going to need 2 vectors. What's the basis for the column space of U?
One, 0, 0, and negative 1, 2, 0?
Yeah, you just look at the pivot columns. Take them. If you want to sort of beautify things, instead of taking 1, 0, 0 and minus 1, 2, 0, you can just take 1, 0, 0, 0, 1, 0, because these are still linearly independent. That would suffice as well. But if you don't want to sort of keep moving things around, you can just take the pivots. Okay. What is a basis for the column space of A?
It's the first 2 columns.
That's the point, exactly. So you look at the pivots, the pivot columns, okay? These 2 columns are not going to be, in general, a basis for the column space of A. But what you can do is you go back to A itself and take the corresponding columns. So you take this and this. If you take these 2, that's a basis for the column space of A.
Would that still hold if you did a row swap during the row reduction?
Yes.
You also,
Yes.
you wouldn't need to row swap those same rows in A?
No. No. Well, there's some dissent about this. Let's take some time. We'll talk about this a little bit, okay, in a second. So I guess I'm just letting this go then, okay? It's better to look into this. Okay, we'll try to talk more about this equality. But let's take that for granted for now. How about a basis for the null space of U? This, you see, null space is slightly trickier to compute. You're going to need to do some sort of solution. You're going to have to set up an equation, and you're going to have to solve that equation. So to figure out the null space of U, I'll just underline this, or I'll put like an orange star. Well, you're going to have to set up the equation ux equals 0 and solve for x. Okay. The point of using this u is that this is already in a nice shape. So I'm just going to open this up. Let's do this slow so that we can review matrix-matrix multiplication also. I'm just going to substitute the corresponding matrices. Okay, when you're multiplying 2 things, I don't care if one of them is a vector. This works all the time. The left matrix, you turn into a bunch of rows. You split into rows. Okay. And then the right one, well, you just turn into a column. In this case, there's only one column, so not much to do. And then how I imagine it is that I take each of these rows, turn it around, and sort of multiply, and then add everything together. So for instance, when I do this matrix vector multiplication, in the first entry I get, and in fact I'll start with this, right-hand side, 0, 0, 0. I get x1 minus x2 plus 5 x3. Okay? I just took the first row of u, multiplied it against the first, well, the only column of x. Make sense? You keep going like this. It's like the third row, for instance, I know is going to be 0 because this is 0. The second row is going to be 2 x2 minus 3 x3. Now the one trick perhaps is to realize, just like you can vector add and scalar multiply to combine a bunch of vectors, you can go backwards as well. So you can start with something that looks more complicated and split it. Okay? And so I'm just looking at x1, x2, and x3. These I want to think of as scalars, and I want to take them out and use them as the scalars in a linear combination. So when I do that, I see this. Okay. Plus x2 times minus 1, 2, 0, plus x3 times 5 minus 3, 0. Any questions about this? I did something similar yesterday too, but after class some of your colleagues sort of asked me about what is happening here. So the right-hand side is a linear combination. That's how you add everything and put them together, right? Which means that if this is equal to this, you can go backwards as well. I guess now I see a little bit why perhaps what I was doing yesterday was a little bit confusing. Let's see. I'm trying to get a basis for the null space of U. So somehow I know that the nullity of U is 1, which means that for the basis of the null space, all I need is one vector that is non-zero. 0 vector is already in that. So 0 vector already solves it, right? So if I were to plug in 0, 0, 0, this would be 0, so it would solve. But I need a non-zero vector because, remember, if you have in your set a 0 vector, it's going to fail to be linearly independent. So you cannot use the 0 vector. You need to use some other vector. So this basis is going to be like this. It's going to have one vector in it. Let's see. I'll tell you how I like doing things. Instead of going in this direction, which is not false, what I say is this. If x1, x2, x3 solves this equation, then I basically open up this left-hand side, and I try to sort of do substitutions using the free variables. So in this case, the third variable is the free variable. Yeah, because the first two are the pivots. Free means non-pivots. First two are not free variables. The third variable is the free variable. So I'll write it perhaps. So x1, x2, these are pivots. Free is the same thing as non-pivot. Variables is just x3. The number of non-pivots is going to match with the nullity. The number of pivots is going to match with rank. So once I determine which variables are the free variables, I'm going to start with an arbitrary vector that solves ux equals 0. And I'm going to try to substitute so that instead of the bound variables, in other words, pivot variables, I see only non-pivot variables. And so how I say, what I do is this. x1, x2, x3 fits into this equation if and only if x1, x2, x3 is something. You see, I don't do anything with this free variable. But looking at the first equation that I erased over here, x1 minus x2 plus 5x3, I know to be 0. Which means that solving for x1, I can do things. And in fact, I might as well just start with the second one. The second row tells me that 2x2 minus 3x3 equals 0. OK. I'm going to take it slow. Writing again what I erased, I get this. This was what I had written before. But in order for two such three-dimensional vectors to equal to each other, the corresponding entries should match, which means x1 minus x2 plus 5x3 is 0, and also x2 minus 3x3 is 0, and x3 is free. Solving this guy, or let's first start with this. Solving this for x2, I can get rid of x2, and then substituting everything into this one, I will get an expression for x1. So you want to go from bottom up if you have this echelon form. So x2 then is 3 over 2 x3. I just solved this part for x2. And then x1 is x2 minus 5 x3, which if I do the substitution once more, I get 3 over 2 minus 5 times x3. Which, if you want, you can simplify this a little bit. And you get this. So you see, why did I do this? Well, I wanted to write down the pivot variables, the bound variables, x1 and x2 in this case, in terms of the free variables. In this case, that means I want to come up with a proportionality relationship between x2 and x3 and x1 and x3. I'll just write it here. So x1, x2, x3 solves ux equals 0 if and only if, well, x1 is minus 7 over 2 times x3, and x2 is 3 over 2 times x3. And x3 itself is whatever number you want. Okay? And so, once you have these two expressions, you go back to x1, x2, x3, and substitute. So instead of x1, I'm going to write minus 7 over 2 x3. Instead of x2, I'm going to write 3 over 2 x3. I don't get to do anything with x3 itself. The point here is that this is a scalar multiple of something. So x3 times minus 7 over 2, 3 over 2, 1. Okay? So this one vector is a basis for the null space. If you don't like fractions here, you can multiply everything by 2 so that you have a nice integer vector. So that you have this one. Yeah.
Why is it that that works to find the basis for
Well, maybe I can say something like this. Any basis vector, by definition, has to satisfy this equation. Because if I'm looking at a basis for some subspace, it's going to be a set of vectors in that subspace. By definition, then, any vector in the basis has to solve ux equals 0. That's first. And I also know that the dimension of the null space is 1, which means that if I'm looking for a basis for the null space, I'm going to need to come up with exactly one vector that is non-zero. Okay? Then I go back to this equation, and I sort of do some math, essentially. Rearrange things and so on, and I try to come up with a relationship these components has. Ultimately, that's what I'm doing here. Like, in order for x1, x2, x3 to be a solution to this, any solution to this has to satisfy this, and this is what I'm saying. And so that means that if I were to then plug in these two equations into this typical form, it's going to turn into this, which is going to turn into this. But then this literally says x1, x2, x3 is a solution to this if and only if it's a scalar multiple of this one vector. In other words, x1, x2, x3 is in the null space of U if and only if it is in the span of this. So this one vector spans the whole null space. And that's all I need. Does that kind of answer?
Yes, it does.
Okay. I think you asked the same question yesterday too, but I.
I just need a reminder.
Okay, okay. No, I said something else yesterday. So yeah.
If the nullity was 0, would we just say that there's no basis for the null space?
Well, you're not going to like this, but you would just say the basis is sort of the empty set. Like, because nullity of U is 0 would correspond to saying that, well, the subspace is 0-dimensional. So since also the dimension is the number of basis vectors you need to have, that means that it has a basis, but it has 0 vectors in it. Comments or questions about this?
If you had 2 free variables, you would need to do something similar, except then you would have your 2 free variables would be in front of 2 vectors.
Yes, exactly. So if I had two free variables, what would have happened is that I would have done this, solve the non-free variables in terms of the free variables, and then I would eventually come up with a linear combination such that the free variables end up being the scalars. Yeah. Okay, so that's the basis for the null space of U. How about a basis for the null space of A? Got this. Just by the same reasoning, nullity of A is the same as the nullity of U. So I'm going to need one vector exactly. It has to be non-zero. The way to fast forward is, okay, when you do row reduction so that you transform A into U, this, and this are preserved. The only thing you need to worry about is this and this. So once you compute a basis for the null space of U, same vector is going to work here. Okay. Just to verify, again, we still have this to talk about, but we'll get there. How can I verify this? Well, the nullity is 1. I know that I'm going to need exactly one vector. So all I need to verify is that A, when multiplied by this, gives me the 0 vector. Okay? Like so. Okay, same business. This by this minus 7. Let's do this slow. This by this is minus 3. This by this is plus 10. So that's going to give me 0. This by this is minus 14. This by this is 0. This by this is plus 14. This by this is 21. This by this is minus 15. This by this minus 6. I was worried it wasn't going to work for a second. So it is 0. You see? There are certain sort of mysterious things happening underneath the hood. And you're right to question why things work. I try to avoid sort of giving sort of because of this type of an answer, because the standard way to answer such questions is to give the proof. But then what's going to happen is that what ends up happening is that you see the proof and you agree with every single step, but it still doesn't make sense. Okay? So the best way at this stage to convince you that XYZ works is to just do a bunch of examples and build the empirical evidence. Okay? Yeah. It just doesn't help. And ultimately, the proofs, too, are not that different from the actual calculations. The only difference between a proof and a calculation like this is that you do the same calculations, but you take every number to be anonymous. Every number is a letter now. You still do the same calculations ultimately. You just need to sort of manage a bunch of indices and stuff. In my opinion, doesn't make things more clear, just looking at the proof, often, at least at this stage. Any comments or questions so far? So, we still have this to discuss. I told you that, first look at the reduced form or just an echelon form. in any event, figure out which columns are the pivot columns, and take those pivot columns in the original matrix. I told you, when you take the pivot columns in the original matrix, that's going to give you a basis for the column space of A. What we can do is, at the very least, we can verify. Okay. Ultimately, if you were to just use the definition of the column space of A, you would just define it to be the span of all columns. You know the rank of A is 2. And so if you were to look at the span of all these 3 vectors, you should say to yourself, OK, exactly one of these 3 vectors is redundant here. That's what you should say. The point is to figure out which one. What I'll do first is verify that indeed these 2 constitutes a basis for the column space of A. Then I'll try to justify why this actually works. Probably 10 minutes is not going to be enough. Let's just verify, at the very least, that this is a basis indeed. To verify blue star, we need to do 2 things. Okay? We need to show, by way of calculation, that first of all, these 2 are linearly independent. Second of all, they span the whole column space. So let's start with whether or not these 2 things are linearly independent. How do you verify a set of vectors is linearly independent? Well, you take a linear combination of them that you call is the 0 vector, and you want to do some math and conclude that ultimately the scalars that you used in your linear combination were all 0 to begin with. So C1 times 1, 2, minus 3 plus C2 times minus 1, 0, minus 5 is 0, 0, 0. Start with this. Solve for C1, C2. For linear independence, you want to conclude that C1 has to be 0 and C2 has to be 0. Doing this linear combination business, we have this. And minus 3 C1 minus 5 C2, saying this is equal to 0, 0, 0. Now to see, this is where sort of you need to develop some experience. When I look at this, I immediately first focus on the second row. Say, oh, if I have this, C1 has to be 0. But if C1 has to be 0, plugging it into this, C2 has to be 0 also. Okay. I just, by intuition, sort of gravitate toward rows that look simpler. Because I know that if I were to look at those simpler rows, I can probably get some more information and sort of simplify the other rows using that new information. Okay, so linearly independent, yes. How about span? Well, by definition, the column space of A is the same thing as the span of this, the other thing. So if you can verify that the third vector is a linear combination of these 2, you would be done. Why? Because that would tell you that, oh, okay, the first two vectors are, first two columns are linearly independent, and then the third column, in fact, is redundant. That's what you would justify doing this. Span. So now you want to solve this guy. First column, second column. Now I'm going to take on the right-hand side the third column. Minus 3. Okay. And again, because there's a 0 here, I immediately think about this entry over here. Because the only way this can have a solution with a 7 here is if C1 sort of compensates for that and adjusts this number to a 7. In other words, if this is to have a solution, C1 has to be 7 over 2. Okay? Okay, now you plug everything in and try to see if you have a solution for C1, C2 also. And so 7 minus 21 over 2 plus minus C2, 0, minus 5, C2. And in fact, you can just combine them into one matrix like this. 0, minus 5, C2. You're asking, can this be equal to this guy? Okay. So you see, if I were to just look at the first row, it says that C2 has to be this minus 5. Minus 3 over 2, that is. But then I would need to take this and plug it into this to verify that indeed it solves the equation. In this case, minus 21 plus 15 is 6. 6 divided by 2 is 3. Sorry, with a minus, of course, because this is larger. So it does solve. So you see the third column is indeed a linear combination of the first two. So it spans everything also. Yeah.
How did you know that C1 was 7 over 2 again?
Because I immediately looked at this 0, okay, and then I said to myself, if I want the second entry to be 7, there's no way I'm going to be able to do anything using this. This doesn't do anything, which means that the only way this 7 can happen is from this. But because this is 2, C1 has to compensate for that too. Oh, yeah, yeah, you would do ordinary reduction if you didn't have a 0. Exactly, very good. Okay. Any comments or questions about this? So as you notice, the more we advance, in a sense, we have like the more tools we have to not ultimately do row reduction. Like ideally, as you keep learning linear algebra, you should be doing as few calculations as possible. Okay, try to do something like that. Yeah.
So for the span part, what exactly was like the original question? Was it just determining if those two were the span?
Yes. Yes. For this equality, I use this idea that row reduce, take the pivots of the original guy. But then I wanted to say a couple words about why that actually works. I didn't discuss why it actually works, but at the very least, I verified that it is true. it is true that this trick works. The perhaps philosophical and sort of cryptic reason why this works is that when you row reduce a matrix, if you start with A and turn it into this, somehow, even though the column space is not preserved, the linear relationships between columns are preserved. It's a bizarre thing to say. But what I'm trying to say here is that if I were to take the exact same numbers, 7/2 for the scalar next to the first column, first pivot, and minus 3/2 next to the second one here, that would give me the third one. Okay? So in a sense, whatever linear relationship the columns of A has, the exact same relationships the columns of U also gonna the columns of U are also gonna have. Okay? So plus so take this C1 and take that C2. So for instance, 7/2 from here plus 3/2 here. In total 10/2, that gives you a 5. See? So somehow, when you do row reduction, the vectors might change, but the sort of general format of the linear combinations don't change. The scalars in particular stay. That's ultimately the reason why this method of, oh, look at the pivots of the reduced one, go back to the original matrix and take the corresponding columns of that original matrix trick works for the basis of the column space. Okay. Okay. Any other last minute questions? Yes?
Do we have to check for linear independence and span each time?
No. So the grading method is going to be typically that I'm not going to ask you to check things, but if your calculations are wrong and you didn't check also, then I'm going to be a lot more punitive. Okay? So either you did your calculations and you trust yourself, or you better check what you did. Okay. That's it. And we'll have our midterm Friday. I ended up not talking about the elementary matrices, but we'll talk about it some other time.